Welcome everyone to our meetup tonight. It's Learning with the Machines. I have the pleasure of introducing my friend Paco Nathan, who's here to talk to us about his latest endeavor, graph-based data science and machine learning. And we're looking forward to that. So, Paco, the floor is yours, and yeah, have a good one.
Thank you. Thank you very kindly, George. I'm grateful to get to present and really super impressed by the lineup and the talks here. This talk is graph-based data science. It's an introduction to, as George mentioned, we'll be doing a masterclass tomorrow. There's a library in Python, an open source library, that provides an abstraction layer for a lot of other libraries regarding graph types of work. And so what we're trying to do is basically make those different libraries provide a common ground so they can communicate together. So that's what I'm going to talk about in the overview of the session here, but then we'll be digging into hands-on coding work with it tomorrow. Also, I should mention all these slides are online, and I'll post a link for that later. Well, so these slides here have a lot of links in them. I kind of err on the side of having too many links. So they're all online. And if there's parts that are of interest, hopefully you can chase down some of the links to find out more about that. Just briefly who I am, a little bit of a bio here. I made the mistake, I was warned not to do this, but about 40 years ago, I decided to study AI in graduate school. And in particular, I spent a number of years working in research and development of neural networks, especially hardware accelerators for neural networks. Then later on, I got involved with something very new that friends were trying out that sounded crazy. Turned out it was named AWS. Of course, I worked on some different open source projects like Spark and Jupyter and now Ray and some others related in that space of data science and led data teams in industry for a number of years. So, introduction. Graph-based data science. Had to come up with a name because I really felt that there was something new happening here. And I wanted to be able to describe what we're doing. So as I mentioned, there is a library, it's open source on GitHub, called kglab. It's an abstraction layer, it's in Python, and it allows you to use a number of other popular graph libraries for doing knowledge graph, but other things like visualization and graph algorithms and inference and all that. So we have a number of community resources, our code, our docs, tutorials like this. There's forums on LinkedIn. There's a graph-based data science forum, and also hosting office hours every month. So just as a high level, there's a lot of community around this. And the question is why? And the short answer is that the kind of workloads that we're seeing in AI applications now, they really do require work that leverages both machine learning models, but also something broader. So when I was in Stanford grad school in AI many years ago, when we talked about AI, machine learning was a tiny, tiny, tiny part of that. And in fact, it wasn't even, in the 80s, machine learning wasn't even considered an academic discipline quite formally by the university. And machine learning models do fantastic work, function approximation especially, but there's a larger context of what needs to be known. And this is where graph work comes in, is providing that context. So I'll try to cover this point from the perspective of some other researchers and commenters. I think there's quite a case for that coming up now. There are other things too. It's just that, it's really taken a long time for this notion of working with graphs as open source, as part of daily practice for data science. It's taken years to get here. I know that when I was teaching, 7 or 8 years ago out in industry, whenever I mentioned graphs, I'd get all kinds of pushback. It sounded too complicated. It sounded too expensive. Everybody would think of like Facebook or Google and really enormous graphs. But the reality is graph problems are all around us, and it is the right way to approach certain problems. And frankly, if you're using spreadsheets, you're using graphs. So I'll try to make that case. The other thing is that, unfortunately, though, there are a lot of libraries, but they're very balkanized, and there's a lot of legacy code. And really, when you dig into some of these libraries, even though they're under current development, they started out from projects in the late 90s. And they started out at a time when people thought things like XML were really great ways to go for technology. Not to disparage XML, but that kind of code that you would see in some of these older libraries, it's not on par with things like maybe Spark or Dask or something more contemporary. So in our project, we have some different focus areas. One is integrating libraries, RDFlib, and the associated, OWL and PyShackle and others. Also for graph algorithms, NetworkX, iGraph, and some others. Certainly that bridges the opportunities to use a number of different kinds of visualization libraries, PyVis especially, but there are others that are allowed by using NetworkX and iGraph as a vector. But then also getting into using PyTorch geometric and Node2Vec, these kinds of things on the GraphML side. But then also shifting over and working with probabilistic graphs, such as PSL Python and PGMPy, etc. Now, while integrating these, there's a priority to make them speak fluently for the popular data science kinds of libraries, pandas, NumPy, scikit-learn, etc. PyTorch also in there. But in addition to doing that, we also need to be able to run efficiently. And so making sure that these tools are integrated with contemporary practices. And what I mean by that is yeah, we can serialize out to JSON-LD or Turtle, but we can serialize out to Parquet, and it's order of magnitude faster. And also it works well with things like Rapids and Spark and others. And frankly, I got into this work with kglab because we were building pipeline components for spacy, for natural language understanding. And we needed a semantic layer for some of the graph work that's being done on graph-based natural language understanding. Okay, and yeah, there's some pain points we keep running into. I do want to be clear that this is all Python under the hood. A lot of it is Python, C++. It's not Java. And the thing is that there's a lot of tools out there in the semantic technology space that are Java. They're kind of old. They may not be supported. They're a bit buggy. They aren't really smart when it comes to leveraging contemporary hardware. I can really make the case for that. The other thing I feel compelled to talk about graph databases. There's a lot of great uses for graph databases. What I'm presenting here is absolutely agnostic about graph databases. And the idea being that the kind of technologies that we're talking about here, the kind of integration work, especially when we talk about pipelines with self-supervised learning, that is not done in graph queries. Okay, that is not about graph databases. So graph databases are important. They're underneath. They handle storage, access, management of data, governance, etc. But what we're talking about is a layer up above them. So we're agnostic to those. And we do integrate with them. Definitely, we've got integration paths with Neo4j, and we're working with a few others. I work pretty closely with DataStax and some others. So this is a lot to chew off, and throughout here you'll see little red markers that say work in progress, but we have knocked down a whole lot of this. So it's quite a constellation of different projects that are integrated, although I'd say that we already have a lot of what's shown here on this particular hub and spoke. And to break it down, here's a diagram that shows in layers, we definitely are taking into account the distributed infrastructure, sort of the cloud computing part of it, if you will. And that's where you get integration of graph databases and cloud storage. And then up above that, being more mindful about data engineering practices, where we're working with Rapids and Arrow and Spark and Parquet, that kind of thing. And then up above there is really the data science part. And so there are some different areas here. Certainly the PyData stack is important, pandas, NumPy, scikit-learn. Also the semantic technologies, RDFlib, etc. Also the graph algorithm libraries, NetworkX, iGraph, etc. But then, getting into the deep learning side with PyTorch and JAX, getting into the human in the loop side, with rubrics and Snorkel and human-learn. The entity linking side with spacy, and also the statistical relational learning side with PSL and causality models, etc. So here, basically, the parts that are in black are implemented. The parts that are in purple are in progress. The parts that are in blue are near term, what's planned out, what we're working toward. Briefly, probably at this mini conference here today, Connected Data London, I probably don't need to make the business case too much because that's a lot of what it's about. But briefly, I'll talk about the business case. So when we talk about data, most people think of data as tables. They think about rectangles, rows and columns, a matrix, a grid, a plot. They think about spreadsheets. They think about reporting tables. They think about relational databases and SQL. And, that's very true. A lot of the world's data is tables, except when it's not. Part of the problem is that when you're working with spreadsheets, and to put this into context, you look at like the Global 2000 and their last mile of reporting for the world's largest companies. The last research that I heard on this is like 95% of the last mile of financial reporting is done in Excel. So, spreadsheets are everywhere. But inside of spreadsheets, you have this thing called a dependency graph. And even though it looks like a table in the UX, the links between the different cells and the computation that's being done and the links across different sheets and all this, it's a graph. Similarly, when you're working in SQL, if you've ever done any work on building SQL engines or digging into them, you know that there's a directed acyclic graph. There's this idea of a query plan. And similarly, chasing down the metadata, the schema is represented as complex graphs, ERDs. And so, whenever you're working with relational tables, you're working with graphs. And the point that I want to make there is that the metadata and the business rules are the part that suffer if you do not recognize the graph. When the graphs get buried, you get tech debt because the metadata and the business rules for what you're really doing gets obscured. And in the context of things like GDPR, that starts to become rather important. So graphs are a good thing, and it really helps to make sure that your IT practices are up to speed. It helps to avoid service failures, project delays, compliance issues, security risks, etc. And kind of as a proof point here, if you've been seeing the prognostication coming out of Gartner research, even as late as like mid-2020, Gartner was saying that knowledge graph was headed toward the trough of disillusionment. But they did a reversal. They did an about face in February, and there's a new report out from Gartner, and a killer line here saying that graph technologies they consider to be in data analytics about 10% penetration in 2021, and they're fully expecting this to go through rapid growth, hitting 80% of data and analytics innovations by 2025. So we're going to see this large uptick in graph technology adoption over the next 4 years. This is what Gartner's saying. Like I say, it's an about face for them. I really recommend this report if you have access to it. They're really making the case. And again, by exposing metadata and business rules, the very thing that gets obscured by using things that claim not to be graphs, but actually are graphs, such as spreadsheets and relational databases. And if you don't believe me, go back to the original papers from Cobb, which is where relational data projections came. SQL was based off of his work, Edgar Cogg. Read some of that. There's a lot of interesting notes there about graphs. I work with a close colleague, Ben Lorica. Ben and I do industry surveys, and we typically publish reports. We've just finished our 5th report about AI in healthcare, but we do these things as contrast studies to understand across enterprise for a particular topic, how can we compare and contrast the organizations that are doing well, that have adopted a technology and they're making return on investment, versus the ones that haven't even gotten started. And so if we can look at what's being reported as pain points between them, we get a pretty good idea. And so in a recent NLP adoption survey, we found out that now for NLP work in industry, knowledge graph is reported as the top 4 use case. And you can drill down on this more. done some talks about this, but you know, we're definitely seeing a lot of knowledge graph work across the verticals, and it's not just a Google knowledge graph. That's kind of a misnomer. It's really across most large tech companies we're seeing this kind of effort. I'll definitely point out I'm involved in another series called Metadata Day, and definitely looking at work from DataHub and Edmondson and Marquez and others. This idea of using metadata in a graph context to understand what your dataset usage is. This evolved out of GDPR responses, and it's being used across most of the large tech companies now. Okay, so let me move into a little bit more definitions, and we'll talk about kglab a bit. Shouldn't have to define too much what a knowledge graph is, but you've got links between different entities. These represent relationships. You know, and the thing that I like to explain to people is that if you've ever worked with object-oriented programming and you understand how to leverage class hierarchies, whether they're in, you know, JVM languages like Java or Scala, or they're in Python, or they're in C++, if you've worked with those kind of class libraries, then you already know the basics of working with controlled vocabularies and working with knowledge graph. And I can break that down more, but I find that really clicks with people once they start to see that sort of one-to-one correspondence between object-oriented programming and what we're doing in graphs. And probably another way to say this for the mathematicians in the audience, shapes in a graph equate to data objects in a relational database. So the topological analysis that you get in graphs is sort of how you get into schema analysis in relational. I can talk more about it. There's certainly property graphs, and then there's semantic graphs, and then there's RDF stars, some ideas about getting these to blend together. We're tracking this very carefully because we really aim to be able to support both, at least in kglab. And I definitely want to shout out that you know, there's a lot of reasons to start from different angles. There's the top-down approach of enterprise knowledge graph. These can be too generic. There's the bottom-up approach of working with personal knowledge graph, and I think that this is extremely important, and it's really catching on a lot of traction, and I'm using this myself. I think that in a corporate enterprise context, the middle-out approach is usually more of an effective data strategy for projects because it tends to be more grounded and more tied in with stakeholders. And I've linked to some notes I really liked from Amit Weisner and Phil Taylor. Also, primary sources, there's a really great article if you haven't seen it, but it's in Communications of the ACM. One of my friends, Juan Sequeira, and also Claudio Gutierrez, they have a brief history of knowledge graph. There's also a survey paper last year, Aiden Hogan and about 20 other authors. That's on archive. And one of the foundational papers, a couple of my friends, Natasha Noy and Deborah McGinnis, did the famous Ontology Development 101 paper when they were at Stanford about 20 years ago. And rolling the clock back, one of my favorite scientists in U.S. history is Charles Peirce, one of the most prolific scientists in U.S. history to date. And in 1882, he wrote a monograph about existential graphs. And definitely check it out because you'll see something very reminiscent of today's knowledge graph ideas. Okay, I want to dig into looking at this from a few different angles. And one I highly recommend is Neil Thompson's work out of MIT. There's a great paper he has called Computational Limits of Deep Learning. And in particular, there's a one-page monograph that he has to summarize it and really bring it to the level of like business stakeholders. What he's noting is that if all that we're talking about in AI is just to dump all of our data into a large deep learning model and then maybe build some custom hardware. If that's all we're talking about, then realistically, from an economic standpoint, we're already at a point of decreased marginal returns. And unfortunately, the tech giants, in the sense of the cloud providers, tend to be talking that way. That's where their rhetoric tends to steer this way. So I think that, you know, Neil Thompson, also Mike Mahoney, similarly at UC Berkeley, some of these people who are heavy on the math and heavy on the physics are looking at this and saying, well, we may not be going quite the right direction. I mean, I'm not opposed to large deep learning models. They're very useful, but keep them in context of where they're useful and why. I think another really good comment about this is from someone I admire a lot. One of my heroes, Uli Sattler from UManchester. I really love that department at UM. And Uli did this lightning talk. We were both in the same track recently in a conference where she presented this of machine learning models along with more symbolic, knowledge-based applications. So how can we use complementary approaches, get the best out of both? Because machine learning has exploded, but it's reaching its boundaries, as Neil Thompson and Mahoney and others are talking about. And in practice, this implies a lot of integration work to take the best of both. And it does point more and more toward self-supervised learning. And I'm certainly not the only one talking about Uli Sadler and others, of course, are talking about self-supervised learning as a general strategy, I think you could say. But you know, the idea is, how do we marry all the advances in machine learning with the graph technologies that we have? How do we provide more context into technologies for generalization that get rid of context? That is machine learning. And so self-supervised learning is really interesting, because the idea is, if you can take a complex object and represent it, and then start to train supervised machine learning, build models, which, you know, given part of the object, they can predict another part. So sort of, you know, one perspective on a complex object is the input, and the parts that aren't shown are the predicted output. So if you can use supervised learning in that kind of a feedback loop, you can actually begin to have machine learning understand more of the latent details in your data. That is, fill in the blanks. And so this is where you start to integrate complementary approaches. This is where deep learning, together with semantic inference, together with probabilistic graphs, etc., start to really make sense. And Jan LeCun has talked about this in the sense of differentiable programming, what he calls pairing deep learning with reasoning. There's also, you know, discussion about self-supervised learning as sort of the dark matter of intelligence. But this is really part of our guiding light for the kglab project. In the interest of time, I'm not going to go through this too much, but this kind of goes back to the metadata day series of events, where we're talking about having, you know, different data domains, different data frameworks, or different organizations at a lower level, having some kind of knowledge graph as a semantic layer up above to make coherence out of those, and then looking more at AI workloads in terms of, what do they provide to the business case? You know, are they working on policy? Are they working on discovery? Are they working on inference? Are they working on planning and optimization? How do we get to that? Well, there's a lot of discussion these days. You probably read some discussion about service mesh leading toward ideas of data mesh. And then kind of in between, there's a lot of ground for talking about using knowledge graphs in between. I will defer to Joe Hellerstein and Zhamak Dekhani and Sam Ramji and some others making really, really cogent case for that. Also, my Kedrawala of USC has some really good discussions about that. Okay, so what are we doing? When we work with graphs, there's this notion of something called algebraic objects. So we can take part of a large complex graph, reduce it down to a vector, and do some number crunching on that. Or take a graph, make it a matrix, do some number crunching. Or in a more general case, take a complex graph, make it a tensor, do some number crunching. And that's been the kind of work, matrix factorization work, that we've done for a long time in graphs. However, there's a real strong case that we want to be able to blend both the symbolic work on graphs with the numeric work in the number crunching. And, you know, graph algorithms, deep learning, et cetera, they need the numeric representation. But when you're working with natural language or compliance rules or human in the loop, you want to leverage that domain expertise. You want to have explainability. That's the symbolic side. So you need to be able to blend these two. I have a mini book out. Dean Wampler and I are working on one that's in conjunction with Manning and NVIDIA. And part of it, we talk about this idea of thinking sparse and dense. In the data workflows, doing graph-based data science, for instance, there are stages where you have to think in terms of sparsity and how you leverage that versus density. We can go into much more detail if you want to on this, but it's really crucial for how is your strategy for leveraging hardware. So within kglab, we leverage the math to do projections of graphs into what we called subgraphs, and from there into vectors, matrices, tensors. And this is part of the fabric that allows us to integrate, have transformations and inverse transformations to go into these different kinds of libraries and still have a common language rooted in math for them to talk with each other. So this is part of what's going on inside of the library, and it's also part of the strategy for leveraging hardware accelerators. And this really speaks to what we do in general in data science, of this whole process of going from unstructured data to structured data. This idea of managing dimensionality and sort of trade-offs between symbolic and numeric representation, thinking sparse and dense. Okay, so that's kind of the background of what we're working with, the theory, the reasons. Let's talk about what we're really doing. So in terms of graphs, there's the idea of triples with RDF, and there's the idea of leveraging a number of different controlled vocabularies to build up your ontology. I've linked some playgrounds if you want to try out some ideas in RDF. What we do is we really build on top of a lot of the RDF lib capabilities, but we try to abstract those out into ways that are much simpler to use in a data science workflow where you're typically working with pandas and scikit-learn, things like that. We have made a lot of work to support different areas of serialization and also make it more robust and more optimal. So with just a couple lines of Python, you can convert from Turtle to XML to whatever to JSON-LD. Those are all great. They're interchangeable. They have good strengths and weaknesses. But the real news, in addition to these different serialization formats, is Parquet. And we can get order of magnitude better performance by using Parquet. And that fits so much better with the hardware, again, with pandas, with rapids, with all these things. With just a few lines, you can take a complex graph and start to focus on what kind of relationships you want to visualize, interactive visualizations in a few different areas, PyViz, Cairo, etc. And as far as querying, we also make it much simpler to wrap Sparkle queries, where the results you get back are a pandas data frame. As far as validation, I think that this is some of the most interesting parts of what's going on these days with RDF lib, is use of, or RDF graphs, is use of shackle, shape constraints. Again, shapes are data objects, so can we operate on those? It's a way of audit, or you can think of it as like a unit test, if you will, for a graph. It's a way of doing validation and audit and prescription. And the nice thing is that the parts that get kicked out as not passing the tests, those are in turn a graph. So you can do, like method chaining with kglab by applying some rules. And all those other kinds of transforms and whatnot feed into, let's prepare our data, run some graph algorithms. So we support NetworkX, iGraph, but then underneath, cugraph, and other optimizations. Again, list comprehensions, data frames, etc. We try to make this very, very simple for fitting into your Python. And then at the end of the day, what this is leading toward is this idea of leveraging trade-offs in inference. So there are some types of inference, like the more axiomatic ones. They're very analytic. They don't handle uncertainty all that well, but they're very analytic. The whole range of what you get with OWL closures and SCAs, transitivity, etc. But then you can flip it around to another side of the quadrant. What we're doing with deep learning and embedding graph neural networks. It works well with uncertainty. It's not very analytic, but the two complement each other. And often in another part of the quadrant, what's going on with statistical relational learning is completely different. Causality models, probabilistic graphs. The point is that these different types of approaches can be leveraged together to build pipelines. And I know I'm kind of running over time, so I want to push on this. Here's an example of using probabilistic soft logic. We'll cover that in detail tomorrow. But it's a way of having probabilistic rules applied to a graph. You can use it for data quality, for instance. And embedding, we've got a lot of work going on right now with PyTorch geometric to make embedding also just a few lines of Python. I'm not going to cover this too much. This is what we'll be going through tomorrow in the masterclass. There's a worked example. It involves 250,000 recipes from food.com. And we do a lot of work along the way just kind of showing this pipeline of your typical, machine learning workflow based off of graph examples. Okay, having said that, I'll post the link. All these slides are online. If you want to get a hold of me, I'd love to talk. I'm on Twitter, LinkedIn, etc. And here's my page. Thank you very much.
Well, thank you, Paco. I was for a moment worried that maybe we wouldn't have enough time for questions. Well, there's a lot of compliments that I'm not going to share all of them. But there is also one really interesting question, which is also a great match actually for the other masterclass we have tomorrow. So the question is about taxonomy.
Very good.
Samuel is asking, what do you think is the appropriate amount of energy for careful taxonomy development? Building a sound taxonomy can be a lot of work, but allowing automated methods to approximate them kind of defeats the purpose, says Samuel, of the role as crypt hierarchies of classes as guardrails for reasoning. And he asked for your thoughts on that.
Very good. Excellent question. And I think that this is turning out to be in practice of knowledge graph adoption in industry. This is becoming more and more of a critical question. I hear it at very large firms. So just to try to contextualize this a bit, when we build ontologies, when we use controlled vocabularies, we typically don't just use one, we use more than one and stitch them together. And maybe we need to add some extra OWL definitions so that for our specific use case, we can take use of some pre-existing vocabularies, but then customize them a bit for our needs. Okay, so that's defining schema and defining relationships that will be in a graph. And so that's the area of ontology. But then when we populate the graph with data, we do our ingest, we do our representation with those vocabularies. Now we've got our data. So we've got A box and T box kind of notions. But there's a third part that weaves through all of this in between the data and its schema, and that's taxonomy. And that's really a lot of the usage. The taxonomy part is describing, so for instance, if you have a product catalog, and you're selling aircraft parts to Airbus, I don't know, some manufacturer, trying to understand where different parts could be a replacement of another part. It's actually very, very critical. And that metadata, can be a life or death matter if it's not correct. So taxonomies are super, super useful, especially when we get into discovery, like search engines, but also drug discovery and other areas, supply chain analysis, things like that. So taxonomy is really kind of this third pillar of what we see of knowledge graph construction. And I just want to emphasize that, the idea of taxonomies, but also thesaurus, maybe in a more general case, it's something that weaves through that interaction of like metadata and data. And getting it right is so important. I think that, my overall impression of the W3C standards, semantic technologies, is that they really do show that, they started out in about 1997, and they really do show like XML is a good idea. They tend to be very analytic, but rather brittle, arguably a lot of them, when it comes to having to work with uncertainties. And unfortunately, in graphs, we run into uncertainty a whole lot. However, the idea of machine learning is to leverage uncertainty, because uncertainty is where you have business opportunity. So what I'm trying to describe is like, making the business case for leveraging uncertainty. That goes back to like Phil Knight 100 years ago, Business 101. Uncertainty is something that we can handle very effectively when we work with probabilistic graphs. There are some ways of also working with uncertainty with deep learning, like you can train embedding models, but then flip them around using the statistical oracles. And so we can come up with like analytic methods there for working with uncertainty. What I'm saying is that taxonomy is an extremely important area, but the W3C technologies kind of, as you've mentioned, tend to be rather crisp. And they need to be, ultimately. But when you're developing and bringing in different work, various sources to build up your graph, you may have some inconsistencies, you may have conflicts or different areas that must be resolved. And this is why I'm such a fan of sort of this compare and contrast of different technologies. Can we leverage probabilistic rules Can we leverage semantic rules like shackle? Can we understand topological analysis leading to generating shackle rules? Can we do the math and leverage the machine learning so that at the end of the day, we come out with a solution that has that kind of crispness, that can do semantic inference, that requires, let's resolve some of the inconsistencies first. So I see this as an iterative process, much like we do with all data science work, all software engineering. It must be iterative. I see the standards for taxonomies as being very important. I leverage SCAs a lot, for instance. But I do see these other complementary technologies as being a missing part of the puzzle. We can talk more about that later on. I know I'm coming up on time, but I really want to address this question because I think it's super important.
Yep, thanks. And yeah, we're out of time, so we have to be wrapping up. And well, hope to see many of you tomorrow at Paco's masterclass. And well, right now, going to the next talk. So Tara is waiting for us. See you in a bit.
Thank you. Thank you very much.